Picture the park in the middle of New York just before dawn. On the lawn there is a cube, 800 meters on a side, and inside it, pressed gently together, is every human being alive. It is shorter than the towers around it. You could walk its entire edge before your coffee went cold. That is the whole species gathered, casting an ordinary shadow. And it is nowhere near the smallest we get. Squeeze out the empty space already sitting inside those bodies, and all 8 billion of us fit into a sugar cube. Yet raise one hand in the dark tonight, and you are holding more atoms than there are stars in the visible universe. Every star behind every star, outnumbered by one hand. Somewhere between the sugar cube and the sky is the real answer to how small we are, and it is not the answer you've been given. By the end of tonight you will have it, 3 times over, and the third answer is not a number at all. Get comfortable. If you enjoy having your sense of scale quietly taken apart, a quick like and subscribe helps this channel reach more curious minds like you, because by the end of this, the word small will not survive the night. Now let's gently drift into this. On February 14th, 1990, a spacecraft the size of a small car turned around to take a picture of nothing in particular. Voyager 1 was about 6 billion kilometers from home that day, past the orbit of Neptune, moving away from the Sun at 17 kilometers every second, and its cameras had not been used in years. There was no scientific reason to switch them back on. Every target worth photographing was long behind it. But one astronomer had spent nearly a decade asking for this photograph anyway, and on that day, the request finally worked its way through the machinery of a space agency and out across 6 billion kilometers of emptiness, and a camera that had been designed to study the clouds of Jupiter swiveled slowly back toward the inner solar system and began to shoot. The astronomer was Carl Sagan, and he had first proposed the picture in 1981. It took 9 years of persistence to get it taken. There were arguments about camera heaters, about budgets, about whether pointing the optics anywhere near the sun might damage them, about whether a photograph with no scientific value was worth the engineering time of a flagship mission. Sagan's answer, in essence, was that the photograph had no scientific value at all, and that this was precisely the point. He wanted a picture of Earth from the edge of the planetary system, not to learn anything about Earth, but to learn something about us. In the end, the spacecraft took 60 frames, a mosaic that engineers later called the family portrait. The solar system photographed from inside its own attic. 6 planets made it into the sequence. Mercury was lost in the glare of the sun. Mars dissolved into scattered light. And in one frame, caught inside a pale band of light stretching diagonally across the image, there was a dot. The dot was Earth, and it was smaller than a single pixel. Measured carefully, our planet occupied about 0.12 of 1 pixel in the frame, roughly an eighth of the smallest unit of the image. The band of light it sits in looks like a sunbeam, and it has been described as a sunbeam ever since, but it is actually an artifact. Sunlight scattering inside the camera's own optics, a flaw in the instrument, a smudge of glare. Earth happened to be caught inside it by chance. Everything anyone had ever done, every city and every ocean and every war and every summer afternoon, was sitting inside a lens flare, 1/8 of a pixel wide. Sagan spent the rest of his life explaining what that dot meant, and the sentence everyone remembers is the gentlest one, a mote of dust suspended in a sunbeam. "That is here," he said. "That is home. That is us." The photograph became the most famous statement of human smallness ever made. It gets printed in textbooks and read at funerals. It is, for most people, the final word on the question of our size, the place where the zoom out ends and the humility begins. And shortly after the sequence was taken, Voyager's cameras were switched off for good, to save power for the long interstellar cruise. No camera has ever looked back at Earth from farther away. The picture was reprocessed in 2020 for its 30th anniversary, with modern software and 3 decades of new technique, and Earth is still under a pixel. That dot is the farthest self-portrait our species has, and it will hold that record for a very long time. There is one more detail from that day worth keeping, because it says something about the distances involved before we have even begun. The 60 frames were not beamed home in an evening. They were recorded onto the spacecraft's tape machine, and then trickled back to Earth over weeks, through the spring of 1990, because at 6 billion kilometers, even radio, travelling at the speed of light, needed 5.5 hours for each one-way trip, and the signal arriving at the great dish antennas was fainter than a fraction of a billionth of a watt. Engineers reassembled the portrait slowly, frame by frame, like developing film from a camera that had been mailed back from the edge of the map. The most famous picture of the Earth took months to come home from a place we still think of as our own neighbourhood. Here is the problem. The most famous photograph of our smallness was taken from inside our own solar system. 6 billion kilometres sounds like an enormous distance, and by the measure of a human life it is. But light, the fastest thing there is, crosses that entire distance in about 5.5 hours. The photograph that made humanity feel small was taken from 5.5 light hours away, and the universe we can actually see extends in every direction for 46.5 billion light years. Compare those two numbers honestly, and the pale blue dot stops being a picture of the universe's scale and becomes something much smaller, a picture taken from the front porch of a house by a camera that never left the yard. There is a clean way to say how much of the story that photograph actually told, and it is worth saying carefully because the whole of tonight hangs on it. Imagine the full range of sizes in the universe as a ladder of size where every rung is a step of 10. Climb one rung and things are 10 times larger. Climb 2, 100 times. 3, 1,000. It is the only honest way to hold sizes this different in one mind at once, and it will be our instrument for the next 2 hours. From a human being up to the edge of the observable universe is a climb of about 27 rungs. The pale blue dot, for all its fame, covers roughly the first 5 of them. The photograph that defined our smallness sampled less than 1/5 of the climb, and then everyone stopped climbing and called it the view from the top. But that is only half of the emission, and it is the smaller half. Because a ladder has 2 directions. Every scale documentary ever made, every zoom-out video, every planetarium show that ends with the Earth dissolving into the dark, they all point the vertigo the same way, up and out toward the galaxies. The pale blue dot only looks outward. The famous zoom only runs one direction, and it turns out, and this is the part that almost never gets said out loud, that the ladder of size does not stop at your skin. It continues downward, through you, into you, rung below rung, and the direction nobody photographs is not the shallow direction. Hold that thought exactly where it is. We will spend the whole night walking toward what it means. So let us ask the real question, the one the photograph was supposed to answer and never quite did. How small are we? Not poetically, not as a feeling, as a measurement. If you took a human being, your height, your weight, the actual volume of your body, and placed it honestly against everything that exists, what would the number be? It seems like the kind of question that should have been answered 100 times in all those documentaries about the size of the universe, and yet almost every telling stops at the feeling, the dot, the hush, the humility, and almost none of them finish the arithmetic. Tonight we are going to finish it. By the end of tonight you will have not one answer but 3. One that will make the pale blue dot look generous, one that no documentary ever told you, and that changes what the first answer means, and a third that is not really a number at all, and is, I think, the reason this question is worth asking in the dark before sleep. I will not pretend the answers are comforting exactly. The title of tonight's journey is honest. What we find is stranger, and, in a quiet way, more frightening than the story we were told. But frightening is not the same as bleak, and the third answer, when we finally reach it, turns the whole picture over in a way I suspect you will not see coming. A dot then, 0.12 of a pixel, resting in a smear of instrument glare, photographed from the near edge of a system that itself will not register as a dot on the next rung of the ladder. A pixel, and then nothing. That is the shape of the story so far, and it is the shape we have all agreed to stop at. One frame, one fleck of light, and then the dark closes over it. Remember that phrase tonight. A pixel, and then nothing. It is going to come back at the very end of this journey meaning something entirely different, and the distance between what it means now and what it will mean then is, more or less, the whole point. But before we can climb the ladder honestly, we owe a debt to the person who built it. Because the ladder of size was not drawn first by an astronomer, or a physicist, or anyone with a telescope at all. The full ladder, top to bottom in one continuous sweep with a human being placed carefully on its rungs, was drawn for the first time by a schoolteacher in a small town in the Netherlands in 1957. He drew it for children. He drew it in 40 steps, and hidden in the last pages of his little book is the observation this whole night turns on, the one the astronomers photographed past, the one the documentaries forgot, the one that has been sitting in a children's book for 70 years, waiting. He noticed where on the ladder the human being actually stands, and it is not where you think. In 1957, in the small Dutch town of Bilthoven, a girl sat in a courtyard outside her school, holding a white cat in her lap. Someone photographed her from directly above. It is an ordinary picture, a child, a cat, a patch of pavement, and it became the first frame of one of the strangest and most influential books of the 20th century. The girl is drawn at 1 to 10 scale. The frame is about 5 meters across. Turn the page, and the same scene is drawn again, but the frame is now 50 meters across, and the girl has shrunk to a detail. The school appears around her. Turn again, 500 meters, and there is the whole neighborhood, the roofs, the roads, again, the town, again, the country. Every page multiplies the width of the view by 10, and the girl with the cat dissolves rung by rung. Town, coastline, planet, orbit, solar system, the local stars, the galaxy, and finally 26 jumps out. A frame filled with pale specks where every speck is a cluster of galaxies, and nothing in the picture admits that anyone, anywhere, is holding a cat. Then the book does the thing almost nobody else had thought to do. It turns around. It comes all the way back to the girl in the courtyard, and it keeps going. Down, into the back of her hand, 10 times closer per page. A mosquito on her skin becomes a monster. Then the skin itself, its ridges like ploughed fields. Then a single cell. Then the coiled machinery inside the cell. Then the huge molecules, then the atoms, drawn, in the style of the 50s, as little planetary systems, and finally the nucleus of a single sodium atom, 13 jumps below the courtyard, a speck inside an emptiness inside the girl's hand. 40 jumps in all, from the clusters of galaxies down to the heart of an atom, with a child placed in the middle of them. The book was called Cosmic View, The Universe in 40 Jumps, and its author was not a scientist. He was the schoolmaster, a gentle Dutch pacifist named Kees Boker, and he built the whole thing as a classroom exercise because he had noticed that his students, like everyone, could not actually feel large numbers. They could recite them. They could not hold them. His solution was to never ask anyone to hold a large number at all, only to take one step of 10 and then another and count the steps. Boke himself is worth a moment, because he is such an unlikely author for the universe's most influential map. He was a schoolmaster who had spent time in prison for his pacifism, a man who at one point refused to handle money at all on principle. He and his wife, an heiress of the Cadbury chocolate family who had given her fortune away, ran a little school in Bilthoven called the Workshop, where the children helped govern, and even the future Queen of the Netherlands was a pupil. He was not trying to revolutionize cosmology. He was trying to teach proportion, in every sense of that word, to children who had just lived through a war. The universe's ladder was drawn, in other words, not by an observatory, but by a classroom, as an exercise in perspective by a man who believed the failure to grasp scale was, at bottom, a moral problem. That is the trick, and it is worth pausing on, because it is the trick this entire night runs on. 1 billion is not a feeling. Nobody has ever felt 1 billion of anything. But 10 is a feeling. A room is about 10 times taller than a cat. A street is about 10 times longer than a room. And Boke's insight was that any size in the universe, no matter how monstrous, is just a chain of those familiar little steps. The ladder of size, the instrument we picked up in the first minutes of tonight, is Boke's 40 jumps wearing a different name. When we say the climb from a human to the edge of the visible universe is about 27 rungs, we are speaking his language, 27 steps of 10, each one as tame as the last, adding up to something no mind can picture directly. The steps are honest even when the total is not picturable. That is the whole method. Boke's little book travelled further than he did. In 1968, the American designers Charles and Ray Eames, famous for chairs of all things, adapted it into a short film, a rough sketch they later remade in 1977 as the 9-minute classic Powers of 10. You may have seen it in a classroom. It opens on a couple picnicking on a blanket by Lake Michigan, a hand, a wristwatch, and then the camera begins to rise 10 times farther every 10 seconds, narrated in the patient voice of the physicist Philip Morrison. The blanket becomes a dot, the city a texture, the planet a ball, the orbits thin, bright rings. The frame fills with the galaxy, then with galaxies scattered like dust. And then, at 10 to the 24th meters, the film famously turns around and falls, back down through every frame it climbed, through the picnic, into the sleeping man's hand, through skin and cell and molecule and atom, arriving at last at the trembling heart of a carbon nucleus. Quarks not yet drawn because the film ran out of certainty. 2 generations of students learned the shape of the universe from those 9 minutes. If you have ever seen any zoom-out video, any app that scrolls from quarks to galaxies, any planetarium sequence that pulls away from Earth until it vanishes, you have seen a descendant of a Dutch schoolteacher's classroom exercise from 1957. But there are 2 things about powers of 10 that almost nobody notices, and they are the 2 things that matter most tonight. The first is where the film stops at the bottom. Its final inward frame sits at about 10 to the minus 16 meters, the outskirts of a proton. In 1977, that was more or less the edge of the known, and it would be easy to assume, watching the film, that the ladder itself ends somewhere near there, that below the proton there are a few more basement steps and then a floor. Here is the fact that should reset your picture of everything. Below the film's final frame, the ladder continues for another 19 rungs. 19 further powers of 10 separate the proton surface from the true floor of physics, a depth nearly as great as the entire climb from the picnic blanket to the galaxies. The Eameses did not stop because the ladder stopped. They stopped because knowledge did. The map has since been extended, and the basement it revealed is one of the 2 or 3 strangest places in all of science. We will stand at the bottom of it before this night is over. The second thing is quieter, and it is Boke's own. In the closing pages of Cosmic View, the pages nobody reprints after the last drawing, the schoolteacher sat down and did the obvious arithmetic that everyone since him has skipped. He counted his jumps, 26 or so going up, from the girl to the galaxy clusters at the edge of the known, 13 going down, from the girl to the nucleus, which was as deep as anyone could then see. And he remarked, in his mild schoolmaster's way, on what the count implied, the girl in the courtyard is not at the bottom of the universe's sizes. She is somewhere in the middle of them. The child holding the cat stands nearer the centre of the ladder than either end. Boke drew from that a lesson about responsibility, that beings in the middle, able to look both ways, owe the ladder some care. And then the book ends, and the world kept the zoom and forgot the observation. Because here is what happened next. The zoom-out became an industry, and the count became folklore that nobody checked. And when, over the decades that followed, physics extended both ends of the ladder, pushing the top out to the true cosmic horizon, and the bottom down and down and down past anything Boke could have drawn, the 2 directions did not grow by the same amount. The ladder we can draw today runs about 62 rungs from floor to ceiling, top to bottom, the full inventory of size that physics can currently name, and the human being no longer stands quite where Boke's gentle arithmetic placed her. The updated answer is stranger than his. Where we actually stand on those 62 rungs, above the middle or below it, nearer the galaxies or nearer the floor, turns out to be the hinge of tonight's entire question, and I'm going to hold it back, deliberately, until we have earned it, because the number means nothing until you have climbed the rungs yourself and felt each one take something from you. So we climb. We start where every honest measurement starts, with the ruler we carry, the only object whose size you have never once had to imagine, and we take the first step of 10, and then the next, and we watch, carefully this time, what the ladder does to us. Fair warning, you will not survive the second rung. Hold out your hand and look at the distance from your fingertips to your shoulder. That is most of a meter, and it is the one distance in the universe you have never once had to imagine, because you have lived inside it your entire life. A human being stands about 1.7 meters tall. A human body encloses about 65 liters of space, roughly the volume of a large travel suitcase, and weighs about 70 kilograms. Those 3 numbers are the ruler for everything that follows tonight. Every monstrous figure we meet from here to the edge of the visible universe is going to be built out of that ruler, one honest step at a time, because that is the only way any of it can be felt rather than merely recited. The first rung of the ladder is the planet under you, and the planet is already beyond picturing. The Earth is 12,742 kilometers across. Divide that by a human height, and the answer is about 7.5 million. 7.5 million people, lying head to toe to reach through the centre of the Earth from one side to the other. Stand them upright instead, a tower of people balance foot on shoulder, and the tower would pass the summit of Everest around the 5,000th person, with 7,495,000 still to stack. By volume, the mismatch is worse, because volume punishes you 3 times over. The Earth encloses about 1 billion trillion cubic metres. Against your 65 litres, the planet outmeasures you by a factor of about 10 to the 22nd power, a 1 with 22 zeros after it. Already, 1 rung in, we have left the range of numbers that human languages evolved to say. Try it from the planet's point of view instead, in case the Tower of People felt abstract. The Earth's surface, its actual skin, the part of it that hosts every landscape you have ever stood in, covers about 510 million square kilometres. A standing human being occupies roughly 1/10 of a square metre of it, the area under your 2 feet. Your claim on the surface of your own planet, the one place in the universe you're unquestionably from, works out to about 1 part in 5 million billion. If the Earth kept a register of what was standing on it, listed by area, you would not appear in the rounding. Whole cities barely would. The lights of every metropolis on Earth, photographed from orbit at night, amount to thin lace on a sphere that is overwhelmingly ocean, rock, and dark. But the number that should genuinely stop you is not about one body. It is about all of us. Picture Central Park in New York, just before dawn on a summer morning. The sky's going grey-blue over the towers on the east side and the paths are empty, and in the middle of the great lawn something impossible is waiting. Every human being alive, all 8.2 billion of us, has been gathered in the night and pressed gently into a single solid block. Every commuter from every city, every child in every village, every stranger who has ever brushed past you, every person you have loved and every person you will never meet, all of them in one cube. Now walk toward it in the half-light. The cube is about 800 metres on a side. It sits comfortably on the lawn. It is shorter than the tallest towers behind you on 59th Street. Their shadows fall across its top face as the sun comes up. Walk its edge at a stroll and you will turn the first corner in about 12 minutes. You could circle the entire human species before your coffee goes cold. Stand back far enough, a few kilometres, the far end of the park, and the cube containing everyone who has ever sent you a message, everyone who has ever had a name, is simply a feature of the skyline, and not the largest one. The morning light climbs down its face. Somewhere in there is everyone. The park holds us all easily with lawn to spare. And notice what the city around the park is doing while you stand there. Nothing. Traffic lights are cycling for empty intersections. A jogger is stretching by the reservoir unaware. The cube does not tower over the skyline. It does not blot out the sun. It casts a shadow no grander than the buildings do. If you had not been told what it was, you might take it for an unfinished development, some new block going up on the lawn. The strangest object that could ever be assembled on this planet, the entire species, present and accounted for, would prompt, from a distance, mild curiosity about zoning. That is the entire species, physically gathered, about half a cubic kilometre of matter. The planet we live on outbulks that cube by a factor of about 2 trillion. When people say humanity has reshaped the Earth, and we have measurably in its chemistry and its climate, it is worth holding this picture alongside. The reshaping was done by a lump that would fit in one city park. As a physical object, the species that weighed the galaxies does not amount to one respectable hill, and the Earth, which erased us so casually, does not survive the next rung. The second rung is the Sun, and the Sun is the first object tonight that most people have genuinely never sized. It looks, in the sky, about as big as the Moon. It is 1.392 million kilometres across, 109 Earths, lined up edge to cross its face. Volume tells it more honestly. About 1.3 million Earths would be needed to fill the Sun. If the Earth were a peppercorn, the Sun would be a ball as tall as a doorway as wide, standing across the room. And on that peppercorn scale, hold this. A human being is far smaller than a single bacterium on the peppercorn skin. 2 rungs, that is all it took. On the first rung you became 1/7,000,000th of the view. On the second, the entire planet became a speck of seasoning, and you became something that could not be found with a laboratory microscope. The ladder has 60 more rungs. Look closer at the Sun's surface, in the images from the solar telescopes, and the scale keeps misbehaving. The boiling texture you see there, That fine golden granulation, like the skin of a simmering pot, resolves into individual convection cells, each one a column of rising and falling gas. Each of those cells, each single grain of the texture, is roughly 1,000 to 1,500 kilometers across, about the size of France. The sun's surface froths with millions of them, and every one appears and dissolves in about 10 minutes, a country-sized bubble with the lifespan of a coffee break. The dark sunspots that drift across the face, the blemishes you can project through a pinhole onto paper, are routinely larger than the entire Earth. Some sunspot groups could swallow a dozen Earths in a row. Nothing about the sun fits the vocabulary of planets. It is not a bigger version of the things we know. It is the first object on the ladder that belongs to a different category of existence, and the ladder is only getting started. There is one more sun number worth carrying with us, because it will matter at the very end of tonight. The sun contains 99.86% of all the mass in the solar system. Everything else, all 8 planets, all the moons, every asteroid, every comet, every spacecraft, every person, shares the remaining 0.14%, and Jupiter takes most of that. The solar system is not, as the diagrams suggest, a family of worlds with a lamp in the middle. It is a star, alone, with some dust that fell into step around it. We live on a crumb of the dust, and the dust barely registers on the star's own ledger. When you sit outside on a clear day and feel sunlight on your face, you're being warmed by an object that outweighs everything you have ever stood on, everything you have ever seen with your own eyes up close, by a factor of about 700 to 1 over the whole rest of its system combined. The sun also converts about 4.3 million tons of itself into pure light every second, and has done so continuously for 4.5 billion years. Set that against the cube in Central Park. The entire mass of the human species equals roughly 2 minutes of what the sun casually burns away. 2 minutes. Every conversation ever held, every book, every hand ever offered to help someone up. The matter that did all of it amounts to about 120 seconds of solar exhaust. This is the kind of comparison the ladder keeps producing, and I want to be careful with it, because it can tip into a bleakness I do not intend, and the numbers do not actually support. The claim on the table tonight is not that we are worthless. The claim is that we have been measuring worth with the wrong instrument, and the proof of that is still 9 rungs away. For now, just log the honest reading. 2 rungs up, and the species is 2 minutes of sunlight. Before we climb on, notice something about how this is going, because the pattern is about to become the story. The Earth did not merely make you small, it made you unfindable. The sun did not merely make the Earth small, it made the Earth a rounding error, a line item in the last decimal place of a star's inventory. Each rung does not shrink the rung below it. Each rung erases the rung below it, wipes it from the ledger entirely, the way the family portrait's 60 frames could not hold Mercury or Mars at all. The pale blue dot was not an unusually humbling photograph. It was simply the first time the eraser was pointed at us from far enough away to work. And here is the open question to carry into the next stretch of the climb. If the sun, 109 Earths wide, 99.86% of everything local, 4 million tons of light a second, is the most absolute object in your sky, the one thing in your experience that cannot be diminished, what do you suppose is about to happen to it? Because the next rung up is other suns, and among them, our sun is not a peppercorn. It is much, much less than that. There is a star you can find tonight. If the sky is clear, that will do to the sun what the sun just did to the Earth. Look for Orion. The 3-star belt is the easiest signpost in the winter sky, and then find the bright reddish point marking the hunter's shoulder up and to the left of the belt. That is Betelgeuse. It looks like all the others, a chip of light, unremarkable, something you could cover with a fingertip. It is a red supergiant somewhere between 700 and 900 times the radius of the sun. Put Betelgeuse where the sun is, and it would not shine down on the Earth. The Earth would be inside it. So would Mars. So, probably, would Jupiter. Our entire familiar neighbourhood, every world any human or any robot we have built has ever touched, with 1 or 2 outer exceptions, would be somewhere in the interior of a single star, dissolved in the thin red weather of its outer layers. And Betelgeuse is not close to the top of the class. Astronomers cataloguing the largest known stars keep a short and slightly disreputable list. Disreputable because measuring the edge of a red supergiant is like measuring the edge of a fog bank, and the error bars are honest and wide. Near the top of that list sits a star called UY Scuti, around 1700 solar radii by the classic estimate, and at or near the very top is a star with the bureaucratic name Stephenson 2-18, whose best estimates run to roughly 2150 solar radii, with real uncertainty and the caveat repeated by every careful astronomer who works on it. Take the estimate at face value, and the numbers stop cooperating with imagination altogether. Placed on the Sun's spot, Stephenson 2-18 would swallow Jupiter's orbit and reach towards Saturn's. Sunlight, the light that takes 8 minutes to reach the Earth, would take about 9 hours just to travel from the star's centre to its own surface, if it could travel straight. By volume, this one star could hold on the order of 10 billion suns. 10 billion. The object that erased the Earth 2 rungs ago, the absolute of our sky, fits into the current record holder the way a single grain of rice fits into a road tanker. There is a strangeness about these giant stars that the word big completely fails to carry, and it is worth knowing because it previews something the ladder does again and again. Past a certain size, objects stop being more of what they were and become something else. A red supergiant is not a larger sun. Its outer layers are so distended, so thinly spread, that their density is lower than the best vacuum most laboratories on Earth can produce. If you could somehow fly a ship across the boundary of Stephenson 2-18, there would be no surface to strike, no moment of arrival at all. Instruments would simply report gradually that the emptiness around you had begun to glow and was warming. A star 2,000 solar radii across is, by any everyday standard, a shining vacuum, almost nothing, spread across a volume that could drink 10 billion suns, held together so loosely that astronomers genuinely struggle to say where it ends. That is why the fog bank error bars exist. The largest objects on this rung of the ladder are barely objects, and they are not even the heavyweights. Here is a distinction that surprises almost everyone. The largest stars are not the most massive stars. Stephenson 2-18, for all its 10 billion solar volumes, probably weighs something in the range of a few dozen suns. Its bulk is dilation, not substance. A star swollen at the end of its life like embers fanned to their widest glow. The true heavyweights, stars of 150 or 200 solar masses, are compact, furious blue objects that would look almost modest beside it. Size and mass, which march together in all of everyday experience, bigger things are heavier things, quietly separate on this rung and go different ways. Keep that divorce in mind. Near the bottom of the ladder, at the very end of tonight's descent, the same divorce is going to reappear in a far stranger form inside your own body. It is worth pausing to feel the specific shape of this vertigo, because it is new. On the previous rungs, you were being compared to things, the planet, the star, and losing. On this rung, you're not even in the comparison anymore. The contest is now between suns, and ours lost by a factor of 10 billion, and you are a bystander at a scale war between objects, any one of which erased your entire world without noticing. The eraser has moved up the ladder. It no longer points at you. That is not a mercy. It is the measure of how far below the action you now are. And I will tell you now, quietly, as a promise for much later tonight, that this exact pattern, the eraser climbing past you, rung after rung, is going to turn out to be a clue, not to your insignificance, to something else. Hold the question, how small are we? And climb. Because the next rung erases the stars, every star you have ever seen with your own eyes, Betelgeuse included, every point in every constellation, every star in the summer sky of every camping trip in your life, lives inside one structure, the Milky Way galaxy. The disk of that structure is about 100,000 light-years across, and it holds somewhere between 100 billion and 400 billion stars. The count is uncertain by a factor of 4 because nobody can see most of them. We count a region and multiply, the way you would estimate raindrops in a storm. Most of the galaxy's stars are small, dim red dwarfs that no unaided human eye has ever seen a single one of. The commonest kind of star in the universe is a kind you have never looked at. Read that uncertainty again. The margin of error on our home galaxy's population, the give or take, is 300 billion stars, 300 billion suns more or less, and the census cannot say. That is the kind of bookkeeping the ladder forces at this height. 100,000 light-years is a number your mind will politely decline to picture, so let us use the trick that actually works, Boke's trick, and shrink until something familiar appears. Take the sun, 1.4 million kilometers across, and shrink it to the size of a white blood cell. 12 microns, a dot utterly invisible to your naked eye, a thing you would need a laboratory microscope to find at all. Shrink every star in the galaxy by the same factor, so the whole structure shrinks in honest proportion. Now ask, with the Sun reduced to a microscopic cell, how big is the Milky Way? The answer is about the size of the continental United States. Sit with that exchange rate for a moment, because it is among the most violent on the entire ladder. An object so large that it erased the Earth from the ledger, shrunk to the edge of microscopic invisibility, and the structure it belongs to still stretches from New York to Los Angeles. If the Sun is a cell in a body, the body is a country. And on that map of America, our entire solar system, the Sun, all 8 planets, the entire territory of every space mission ever flown, is a patch about the size of a coin, lost somewhere in the outskirts of one unremarkable county, and the nearest neighbouring cell is kilometres away across open, empty land. Betelgeuse itself gave the world a live demonstration of what these objects are quite recently. Through the winter of 2019 into 2020, the star visibly dimmed, faded to about a third of its usual brightness, enough that anyone who knew Orion could see the shoulder had gone strangely dull. For a few months, headlines wondered openly whether it was about to explode. The eventual explanation was almost more unsettling in its casualness. The star had exhaled. A piece of its own surface had lifted away, cooled into a cloud of dust roughly the size of a planetary orbit, and drifted across our line of sight like smoke passing a lamp. An object at the scale of these giants does not have weather the way a planet has weather. It has weather the way a small solar system would. Burps and plumes with the footprint of worlds. A thing you can cover with your fingertip doing that 600 and some light years over your roof while you slept. Here is what that does to any attempt at a galactic self-portrait. Suppose you wanted the pale blue dot's older sibling, a photograph of the Milky Way with the Sun marked on it. No such photograph exists, and none ever will be taken in any conceivable human future. Every camera we own is inside the galaxy, the way a fish's eye is inside the sea, but set even that aside. Suppose you could print the galaxy's portrait at any size you like. Print it as a poster, print it as a mural on the side of a building, print it if you want at 1 pixel per solar system. At poster size, the Sun's pixel does not exist. The whole solar system is millions of times too small to register. On the building-sized mural, still nothing. To give the Sun a single printed dot 1 millimeter wide, the mural of the galaxy would need to be roughly the size of a continent. There is no version of the family photo in which we appear. On the last rung you vanished from the comparison. On this rung, the Sun itself becomes unmarkable. Not small in the picture, but absent from it, at any physically printable scale, and the Milky Way is one galaxy. The word one is about to do to the galaxy what the galaxy just did to the Sun, and then something is going to happen to the ladder itself, something stranger than growth, a change in the very texture of the universe that almost nobody outside cosmology has ever heard described. It happens about 3 rungs up. It is the strangest thing the upward climb has to show, and it is where the upward climb ends. Not because the universe stops, but because, past that point, the universe stops having places in it at all. Picture the Milky Way now as a single island of light, seen from outside hanging in blackness. A slow pale spiral, 100,000 light-years of stars turning together. It is the largest thing we have met, and on this rung it becomes immediately one of a handful. The Milky Way belongs to a small gathering called the Local Group, a few dozen galaxies, most of them dwarfs, scattered across roughly 10 million light-years, with 2 large spirals, ours and Andromeda, anchoring the arrangement like 2 big houses on a sparse rural road. Beyond the group, tens of millions of light-years further, lies the Virgo cluster, a city of well over 1,000 galaxies that our little road gravitationally leans toward. And beyond and around Virgo, the maps blur upward into structures hundreds of millions of light-years across, walls and sheets and filaments of galaxies surrounding voids of almost perfect emptiness. This channel has walked those particular streets before, and tonight is not the night to walk them again. Tonight they are one rung, taken at speed, because the important thing is not the architecture itself. The important thing is what happens just above the architecture, where the ladder does the strange thing I promised. First, the top of the climb, stated plainly, the observable universe, the full sphere of everything whose light has had time to reach us, is about 93 billion light-years across. In meters, that is about 9 times 10 to the 26th, a 9 followed by 26 zeros. It contains, by the standard estimates, somewhere between 200 billion and 2 trillion galaxies, a census so unsettled that the count of entire galaxies in the universe is uncertain by a factor of 10, and the working figure changed by that factor within the last decade. Each of those galaxies carries its billions or hundreds of billions of stars. Multiply through, and the stars themselves number somewhere between 10 to the 22nd and 10 to the 24th, a range whose customary comparison, more grains than all the sand on all the beaches of Earth, is repeated so often that it has stopped landing. Suffice to say, the beaches lose, and not narrowly. That is the ceiling of the ladder of size, not the ceiling of the universe. Hold that distinction. It returns near the end of tonight with teeth. But the ceiling of what any telescope, any instrument, any mind on Earth can in principle survey. 27 rungs above your bed. If you want to feel the ceiling rather than recite it, there is one photograph that does it better than any other ever taken. In December 1995, the operators of the Hubble Space Telescope did something that many astronomers at the time considered a scandalous waste of the most oversubscribed instrument in history. They pointed it at nothing, deliberately. They chose a patch of sky near the handle of the Big Dipper selected precisely because it was empty. No bright stars, no known galaxies, no gas, a blank between the furniture. The decision was one man's gamble. Robert Williams, then the director of the Space Telescope Science Institute, had a small allowance of observing time reserved for the director's own judgment, and he chose to spend 10 days of the world's most coveted telescope staring at a deliberately empty keyhole. Colleagues warned him the result might be a blank frame and a public embarrassment. 10 days of the instrument that fixed its mirror in front of Congress, spent photographing nothing. Williams said, in essence, that if the frame came back blank, that would itself be worth knowing. The patch was tiny, about the width of a grain of sand held out at arm's length, a keyhole of nothing. And Hubble stared at that nothing, unblinking, accumulating faint light, for 10 consecutive days. When the frames were stacked and processed, the empty keyhole contained roughly 3,000 galaxies. Williams's gamble is now widely considered the most important photograph the telescope ever took. Not stars, galaxies, each one an island of billions of suns, layered behind one another into the dark going back nearly to the beginning of time. Later, longer stares at other blank keyholes found more than 5,000. Do the arithmetic across the whole sky, and there is no escaping it. Behind every grain of sand patch of blackness above your roof tonight, every single one in every direction, stand thousands of galaxies stacked into the distance without exception, everywhere. The sky is not scattered with galaxies. The sky is made of them, the way a wall of static is made of dots, and the darkness between the stars is not emptiness. It is depth. Now, here is the strange thing, the thing the climb has been building toward. You would expect, climbing this ladder, that the pattern we have watched all night simply continues. Structures inside structures, each one erasing the last forever, or at least all the way to the ceiling. Galaxies into groups, groups into clusters, clusters into superclusters, superclusters into something grander still, and so on up. That expectation is reasonable, it is intuitive, and it fails. It fails at a specific measured height. Above a scale of roughly 250 to 300 million light-years, the structure stops. Cosmologists, who are not generally poets, gave the boundary a genuinely haunting name, the end of greatness. Below it, the universe is lumpy. Stars, galaxies, clusters, filaments, voids, all the architecture, all the individuality, everything that could ever be pointed at and named. Above it, the lumps average out, and the universe becomes smooth, uniform, statistically identical from place to place, the way a beach is identical from dune to dune, even though no two sand grains match. Survey a box of universe 400 million light-years wide, then survey another such box anywhere else, anywhere in any direction, however far, and the two boxes will hold, to a good approximation, the same amount of matter in the same general arrangement. No landmark distinguishes them. Nothing about either box says here rather than there. How do we actually know this rather than merely assert it? We know it the slow way, by address book. Since the 1980s, teams of astronomers have been compiling three-dimensional maps of the universe, measuring the distance to galaxy after galaxy after galaxy, first hundreds, then thousands, then, with the great automated sky surveys of the last 25 years, millions of them, each one placed at its measured depth in the dark. The early maps, the first thin wedges of charted universe, revealed the architecture, the walls, the filaments, the great voids, structure grander than anyone had guessed. And then, as the maps grew wider, the architecture did something profound. It stopped getting grander. Wedge after wedge, million galaxies after million, the maps filled in with the same froth at the same scale. Big, but never bigger. Wall after wall, but no wall of walls. The pattern repeating in its statistics like wallpaper, all the way out. The hierarchy that runs from dust grains to superclusters, the nesting that had held for 24 rungs of the ladder, was measured to its end. The universe has a largest kind of thing, and we have seen it, and above it the maps go quiet. I want to be precise about what that means, because it is not one more rung of shrinking, and it deserves to be felt exactly rather than vaguely. It means the universe, viewed at its own full scale, has no places in it. Places, this cluster rather than that one, this galaxy, this street, are features, and features live below the end of greatness. Zoom far enough out to the scale where the observable universe fits in your view, and every feature dissolves into the average. A map of the entire universe, drawn at the universe's own scale, would show a fine, even froth, the cosmic web blurred to texture, like the grain of paper, and nothing else. No brighter patch marking Virgo, no spiral labelled Milky Way, no dot for the Sun, no dot for Earth, and nothing whatsoever for the cube in Central Park. Not because the mapmaker lacked ink or resolution or care, because at that scale, those things are not on the map to draw. They are not features of the universe, any more than a single crystal of salt is a feature of the ocean. The ocean is salty. The ocean has no salt grains marked on any honest chart of it. That is our situation exactly, and no one ever says it plainly. The universe is faintly, uniformly seasoned with galaxies, and we are part of the seasoning. Let that come all the way in, slowly, because it is the upward ladder's final gift and its coldest one. Every earlier rung made you small. Smallness, whatever else it is still a location in the world. A small thing is somewhere, a dot on a map, a mote in a sunbeam. This rung does something different. This rung takes away the address. At the universe's own scale, there is no marker for the galaxy you live in, no marker for anything you have ever seen, met, feared, or loved. Not a small marker, not a faint one, none. You're not written small in the universe's ledger. At full scale, you're not written anywhere in it at all. The dot was at least a dot. Above the end of greatness, there is not even that. And the strangest part, the part to fall asleep on, if sleep is taking you, is that this is not a statement about you. It is a statement about the universe. At its own scale, it keeps no ledger, marks no places, remembers nothing smaller than everything. That is the top of the ladder. 27 rungs, one eraser after another, ending not in smallness but in namelessness. And now that we have climbed it honestly all the way, the climb the pale blue dot never finished, we can finally do what no zoom-out video ever does. We can stop at the top, turn around, look down at the figure in the bed, 1.7 meters of ruler, 70 kilograms, 65 liters, and run the actual numbers, not the feeling, the division. What fraction, exactly, is a human being of everything there is to see? The answer arrives in the next few minutes, and I will tell you now. It is a number no one ever says out loud. It is worse than the dot ever implied. And it is, in a way that will take the whole rest of the night to unfold, the wrong answer. The right answers come after it. Stay with me. Let us stop climbing for a moment, here at the top, and stack the whole ascent in one place, slowly, like setting out coins on a table in the dark. You, 1.7 meters, lying still. The earth beneath you, 7.5 million of you through its middle, its skin so wide your share of it is 1 part in 5 million billion. All of humanity gathered, one cube on one lawn in one park, casting an unremarkable shadow. The sun, 109 Earths across, holding 99.86% of everything local, burning the mass of our whole species every 2 minutes without noticing. The giant stars, one of which could drink 10 billion suns and has no proper surface, only a glowing thinning away. The galaxy, a country-sized structure when the sun is a microscopic cell, its star count uncertain by 300 billion. The local group, a rural road of galaxies, the clusters, the walls and voids, the froth, and then the end of greatness, where the froth smooths out and places stop existing, and above it, the full sphere of the observable 93 billion light-years wide, holding perhaps 2 trillion galaxies behind every grain of sand's width of your sky, in every direction without exception. That is the ladder above your bed. 27 rungs. You have now climbed all of them, which is more than the pale blue dot ever showed you, and you are entitled to what comes next. Because now we can answer the question. The first answer, the honest arithmetic that the documentaries always gesture at and never actually perform. How small are we? Not as a hush, as a division. Start with the simplest version, length. The observable universe is about 9 times 10 to the 26 meters across. A human being is about 1.7 meters tall. Divide. To span the observable universe with human beings, laid head to toe like a measuring chain, you would need about 5 times 10 to the 26 people, a 5 followed by 26 zeros, 500 trillion human beings. To hold that number against something, it is tens of thousands of times more people than there are stars in the observable universe, by even the most generous star count. If every star in every galaxy in the entire visible cosmos were itself a person, the chain would still fall short of one end of the universe to the other, tens of thousands of times over. There have been, across the whole history of our species, roughly 100 billion humans in total. Every person who has ever lived, laid end to end, would reach about 1/100th of the way across a single galaxy's disk, our own. The chain of everyone, ever, does not cross the room. But length flatters us, because length is only 1 dimension, and we live in 3. The honest measure of how much universe a thing takes up is volume. Here is the division that, as far as I know, no scale documentary has ever spoken over its closing music. The observable universe encloses roughly 3.6 times 10 to the 80th power cubic meters. A human body encloses about 0.065 cubic meters. The suitcase. Divide the suitcase by the sphere and you get the true fraction, the actual answer to what portion of the visible universe you personally constitute. The answer is about 1 part in 5 times 10 to the 81st. I want to write that number in the air for you, because the exponent slides past the ear and the digits do not. Imagine writing your share of the universe as a decimal. You would write 0, then a decimal point, then a 0, then another, and you would keep writing zeros, one after the next at 1 per second for a minute, then 2 minutes, zeros, only zeros, and at around 80 seconds, having written 80 zeros after the decimal point, you would finally, at last, be permitted to write a digit that was not 0. That is you. That is the measured, checkable, arithmetic answer to the size of a human life against the visible whole. A decimal point, 80 zeros, and then, faintly, at the end of that corridor of nothing, you. For comparison's sake, the number of atoms in the entire observable universe is estimated at 10 to the 80th. Your share of the universe, written out, has about as many zeros in it as the universe has atoms has digits. The smallness is of the same clan as the largest counting numbers physics ever uses. If the pale blue dot made you feel like a mote of dust, understand that the dot was flattery. A mote of dust in a sunbeam is a giant, visible, locatable, physically there in the beam. 1 part in 10 to the 81st is not a mote of anything. It is a number indistinguishable, for every practical and emotional purpose, from 0. You can run the division through any other quantity you like, and it keeps returning the same species of verdict. Run it through mass, the ordinary matter of the observable universe, just the atoms, setting aside the dark components entirely, comes to roughly 10 to the 53rd kilograms. The human species, all 8.2 billion of us together, weighs about 5 times 10 to the 11th kilograms. Divide, and humanity amounts to about 1 part in 10 to the 41st of the universe's ordinary matter. Not one person this time. All of us. The whole cube in the park. Every hand that has ever built or held anything together. A 1 over a 1 with 41 zeros share of just the visible universe's atoms. Run it through count instead of weight, and it gets no kinder. There are perhaps 10 to the 24th stars out there, So if the stars of the observable universe were shared out equally among living humans, your personal allocation would be somewhere north of 100 trillion stars, about 10,000 stars for every second of a long human life. You could be given 10,000 suns every second from birth to death, and the universe would pay out that inheritance to every person alive and never notice the withdrawal. There. That is the first answer, and it is on the table, and I am not going to soften it. By volume, against the visible universe, a human being essentially does not exist. If tonight's question had only one answer, that would be it, and the title of this video would be Simple Cruelty. Sit with it for just a breath. Let the room be quiet around you. Let the number be as large as it is. There is no hurry here, and nothing about the dark outside your window has changed because we counted it. The universe was this size yesterday. It will be this size, a little larger in fact, tomorrow. The only new thing in the world tonight is that you now hold the actual figure, which almost nobody on Earth has ever bothered to compute. And holding the actual figure is a strange kind of privilege, whatever it says. Breathe once more, because I am now going to tell you what is wrong with it. Here is what is wrong with it. Every step of that arithmetic treated the ladder of size as if it were a flagpole, as if it stood planted at your feet, rising away above you, with you at the bottom looking up. All night we have climbed up and up and up, and every documentary you have ever seen climbed the same direction, and the entire genre of human smallness is built on the unexamined assumption that up is the only way the ladder runs, that a human being stands on the ground floor of existence, and everything else is sky. And you already know, because a Dutch schoolteacher noticed it in 1957, and because I promised you at the start, that this assumption is false. The ladder of size does not begin at your feet. It passes through you. You're standing partway up it, and tonight, for once, we're going to look down. Down past the floor the pale blue dot stood on. Down through the trapdoor the zoom-out videos never open. What is below you, it turns out, is not a basement. It is a second universe, an inward one. And here is the sentence I want you to keep repeating in your mind as we start the descent. It is deeper going down than it is going up. The half of the ladder that no one photographs, the direction with no famous pixel, holds more rungs, more strangeness, and, by the end, a more complete reversal of tonight's question than everything we have climbed so far. The first answer measured you against the stars. The second answer requires measuring what you're made of. And the count down there is not going to come out the way you expect. Turn around then. Look at the back of your own hand. The rest of tonight happens inside it. Raise one hand above your face in the dark and look at the back of it. Now fall. The skin comes up to meet you, and it is not the smooth surface you have looked at your whole life. It is terrain, ridged and furrowed, a dry plain of overlapping plates lifting away in flakes at the edges. You drop through a fold of it, past a hair rising like a redwood out of its shaft, and into the living layers underneath, and here the traffic starts. Cells sliding past one another in ranks, plump and irregular, each one a walled compound. Slip inside one. It is not a bag of fluid. It is a working city under weather, long fibres running like girders, tubes and folded sheets stacked in the middle distance, cargoes being hauled along filaments by molecular machines that actually walk, 1 foot in front of the other, carrying their loads down the corridors. At the centre, the archive, wound and coiled, 2 meters of DNA folded into a compartment a few thousandths of a millimetre across, and read from, constantly, by machinery that unzips it, copies a passage, and zips it shut again. All of that is one cell. Pull back a little and see the ranks of them going off in every direction into the warm dark and understand the count. Not thousands, not millions, 37 trillion of them in the body lying in this bed, and keep falling because we are nowhere near the bottom. 37 trillion is the modern figure. 37.2 trillion from a careful cell-by-cell audit published in 2013, replacing decades of textbook guesses. Hold it against the sky for a second. The observable universe holds, at the high estimate, about 2 trillion galaxies. You're carrying in your own tissues something like 18 times more cells than the visible universe has galaxies. And among those cells, the ones doing the listening right now, the neurons in your head, number about 86 billion. 86 billion. That is not a poetic near match to something cosmic. It is a real one. the same order of magnitude as the number of galaxies in the observable universe on the lower, more conservative estimates. Somewhere between the count of galaxies in the visible cosmos and the count of thinking cells in one skull, the universe has arranged a coincidence that ought to be spoken about more often than it is. The object doing the wondering has roughly as many parts as the sky has islands of stars. The connections between those neurons multiply the count again. Each neuron reaches out to others through junctions called synapses, and the total number of synapses in a human brain is estimated somewhere between 100 trillion and 1 quadrillion. A quadrillion. 1,000 trillion. If every synapse in your head were a galaxy, you would be carrying 500 visible universes worth of them between your ears, and they would all be firing in patterns right now in order to process this sentence about themselves. And the whole apparatus runs on roughly 20 watts. Less power than the bulb in a bedside lamp. 20 watts, 1.5 kilograms, the temperature of a warm bath. That is the specification of the only object in the known universe that has ever mapped the universe. There is a further count that is stranger still, and worth a moment because it undermines a word most people use without noticing. Not all 37 trillion of those cells are you. Living in and on your body, mostly in your gut, are bacterial cells in numbers roughly comparable to your own, something in the same ballpark as one microbial cell for every human one. The old claim was 10 to 1. The careful modern estimate is nearer parity, and either way the picture is the same. A human being is not a single organism standing on the ladder. A human being is a densely populated ecosystem, a walking coral reef, carrying a metropolis of other lives at a rung of the ladder we have not even reached yet. When we ask, how big is a human being, the question already contains a hidden vote about where you end. But cells are still enormous, on the ladder. Keep falling. Below the cell, the machinery resolves into molecules, and the molecules are worth one breath of their own, because the largest of them are as intricate as anything on the upward ladder. A single protein is a chain of thousands of atoms folded into a specific three-dimensional shape, and the shape is the function. Fold it wrong, and it does nothing, or does harm. Your body builds these things constantly, thousands of them per cell per second, each one folding itself into the correct configuration out of an astronomically large space of possible wrong ones in about 1,000th of a second. Below the proteins, into atoms, and here we arrive at the number that should end the argument about our size, though almost nobody has ever heard it. A human body contains about 7 times 10 to the 27th atoms. Say that plainly, because the exponent hides it. 7 billion 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 atoms. Now recall the figure from the top of the ladder, the count of stars in everything we can see, all 2 trillion galaxies of them, out to the edge of the observable universe. That count is somewhere between 10 to the 22nd and 10 to the 24th. Hold those two numbers side by side and let the comparison land in the way it deserves. There are more atoms in your body than there are stars in the observable universe. Not slightly more, thousands of times more, by the generous star count several thousand, by the conservative one hundreds of thousands of times more. Every star in every galaxy in the entire visible cosmos, every sun in the Milky Way, every sun in Andromeda, every sun in every smudge of light in the Hubble Deep Field, every star behind every star behind every star, all the way out to the end of greatness, and past it to the horizon of what light can reach us. Take that entire inventory of suns, the full census of the visible universe, and it does not come close to the number of atoms in the hand you are holding above your face. You could give every star in the sky to a different atom in your body, and you would run out of stars before you had finished your fingers. I want to be careful and honest here, because this is the video's hinge, and the point is easy to overstate. Atoms are not stars. An atom is not a place, and nothing lives on it. And the comparison is a comparison of counts, not of grandeur. Nobody is claiming your hand is more magnificent than the night sky. What the comparison actually does is something more surgical. It demolishes the assumption underneath the entire first half of tonight. We measured you against the universe and got a decimal point and 80 zeros, and we got that answer because we implicitly treated you as a unit, a single small thing, a dot to be compared against a sphere. But you're not a unit. You're an assembly, and the assembly's part count exceeds the visible universe's star count by orders of magnitude. When we wrote your fraction as 1 over 10 to the 81st, we were dividing an enormous number by a more enormous one, and calling the top of the fraction 1. A dot has no inside. You're almost entirely inside. There is one more thing to say about those 7 billion atoms before we go below them, and it belongs here rather than anywhere else tonight. They are not new. Every atom in your body heavier than hydrogen was manufactured, physically assembled, nucleus by nucleus, inside a star, or in the collision of two stellar corpses, and then thrown out into the dark when that star died. The calcium in your bones, the iron in your blood, the oxygen you are breathing at this moment, all of it was made in the interiors we walked past on the 4th rung of the climb, and has been drifting through this galaxy for billions of years, and happens to be arranged tonight into a listener. The upward ladder built the material of the downward one. When you compare the atoms in your hand against the stars in the sky, you are not comparing two unrelated inventories. You are comparing the product against the factory, and the question changes shape as you feel that. How smaller we sounded at the start of tonight like a question about our position in a big room, it is turning now into something else, a question about which direction on the ladder is longer, and what it means to be a thing that has a downward direction at all. Because your inward ladder is not finished. We have gone from body to cell to molecule to atom, 4 rungs, maybe 5. If the atom were the floor, this reversal would be a nice rhetorical trick and nothing more. But the atom is not the floor. The atom is not even close to the floor. The atom is in fact the last thing on this entire ladder that is mostly what you would expect it to be, and it stops being that the moment you look inside it, which is what we do next. Because in 1909, in a darkened room in Manchester, 2 men sat for hours counting faint flashes of light on a screen, and found inside the atom an emptiness so extreme that their supervisor said it was as incredible as firing an artillery shell at a sheet of tissue paper and having the shell come back and hit him. Everything solid you have ever touched, the blanket over you right now, the floor, your own body, has that emptiness inside it, in every atom without exception. That is the next rung down, and below it, the ladder still has more than 20 rungs to go. In a darkened room in Manchester in 1909, a young man sat on a stool with his eye pressed to a microscope, counting flashes of light in the dark. His name was Ernest Marsden. He was 20 years old, and the room had to be black because the flashes were so faint that his eyes needed half an hour to adapt before he could see them at all. In front of him, mounted on a rotating stage, was a sheet of gold leaf about 400 nanometers thick, perhaps 2,000 atoms, thin enough to see a lamp through. Behind it, a small sample of radium was firing alpha particles at the foil like a machine gun. Where they struck a zinc sulfide screen, they made a tiny scintillation, a spark. And Marsden and his colleague Hans Geiger sat in the dark for hours, then for days, counting sparks by eye, one at a time, and writing tallies in a notebook. The experiment was, in a sense, busy work. Their supervisor, Ernest Rutherford, had given Marsden a task that was expected to produce nothing. The atom in the model of the day was a soft thing, a diffuse pudding of positive charge with electrons scattered in it, and firing alpha particles through gold foil should have been like firing bullets through fog, everything passing with slight deflections. But Rutherford, careful as ever, had them look for the improbable anyway, put the screen not behind the foil but in front of it, and check whether anything at all came back. Something came back. Not often, about 1 alpha particle in 8,000, but back, bouncing off the foil at angles beyond 90 degrees, returning toward the source it came from. Marsden reported it, then reported it again after checks, and Rutherford spent months turning the result over before he was willing to believe it. The sentence he later used to describe his reaction is one of the few genuine poems in the history of experimental physics. It was, he said, almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. By 1911 he had worked out what it meant, and the answer changed the shape of matter permanently. There was nothing soft inside the atom. Nearly all of the atom's mass was concentrated in a fantastically tiny core, and the core was so dense and so charged that on the rare occasion an alpha particle happened to fly nearly straight at one, it was slammed back the way it came. The rest of the atom, nearly all of its volume, was nothing at all. Let us put the proportions on the ladder honestly, because they are the point. An atom is about 1/10 of a meter across, 10 to the minus 10 meters. The old comparison still works better than anything invented since. Take an apple and magnify it until it is the size of the Earth, The atoms inside it are then roughly the size of the original apple. That is what a factor of 10 to the 8.5 does. But now go inside the atom itself. Take a hydrogen atom. The simplest thing there is, one proton and one electron, the most common object in the universe. The atom is about 5.3 times 10 to the minus 11 meters in radius. Its proton is about 0.84 femtometers. The ratio between them is about 63,000 to 1, 63,000. Imagine a cathedral, an enormous one, the kind that takes 3 centuries to build. With a nave you could fly a small aircraft down. Now imagine a single fly hovering at the centre of it. That is the proportion of nucleus to atom. And here is the part that breaks intuition. The fly holds 99.97% of the cathedral's mass. All the stone, all the vaulting, all the space, everything except the fly, accounts for less than 1/30th of 1% of the weight of the object. Matter is not made of stuff with gaps in it. Matter is made of gaps, with an almost imperceptible amount of stuff holding the pattern. One correction is owed here, because the cathedral image is right about proportion and wrong about picture. It is tempting, and every diagram on every classroom wall encourages it, to imagine the electron as a tiny ball flying around the nucleus like a planet around a sun, tracing out the cathedral's empty volume with its orbit. That picture is not a simplification. It is simply false, and it was already known to be false within about 15 years of Rutherford's result. An electron in an atom has no orbit and no trajectory. It occupies a standing pattern, a probability cloud with a shape, sometimes spherical, sometimes lobed like a dumbbell or a four-leafed clover, and it does not travel around anything. The emptiness of the atom is not empty space with something flying through it. It is a region where an electron's presence is smeared out, all at once, in a fixed pattern that does not move. This matters far more than a pedantic correction usually would, and it matters tonight, because the false picture, the atom as a little solar system, is the seed of one of the most persistent ideas people have about the ladder of size. We will meet that idea and settle it in about half an hour. There is a lovely footnote to the proton's size which shows you how close to home this ladder still runs. Between 2010 and 2019, physics could not agree on how big a proton is. A team led by Randolph Pohl measured it a new way, by building an exotic version of hydrogen in which the electron is replaced by a muon, a particle 200 times heavier that therefore orbits 200 times closer and feels the proton's size far more sharply. Their answer came out about 4% smaller than the accepted value, and the disagreement was statistically overwhelming, not a fuzzy tension, a flat contradiction between two mature techniques. 4% sounds trivial. In precision physics it was a 9-year crisis, with serious people proposing that some new force of nature might couple to muons differently than to electrons. The resolution, when it came, was mundane and slightly humbling. Newer electron measurements agreed with the muons, the older numbers had been off, and in 2018 the official value of the proton's radius was quietly revised downward. Sit with the plain version of that. Within the last decade, every proton in your body, and there are about 10 to the 28 of them, was officially the wrong size, and it took the world's laboratories 9 years of argument to shrink you correctly. There is a second surprise waiting inside that fly, and it undoes an assumption most people never knew they held. You might suppose that the proton's mass, and therefore, near enough, your own body weight, is simply the sum of the little pieces inside it. It is not. A proton is built from 3 quarks, and if you add up the masses of those 3 quarks, you account for roughly 1% of the proton's mass. 1%. The other 99% is energy, the seething, straining field of the strong force binding the quarks together, converted into mass by the most famous equation in physics. Which means that when you step on a bathroom scale, 99% of the number looking back at you is not substance at all. It is confinement energy, the cost of holding a few nearly weightless specks in a bag they cannot leave. You're not in the main made of stuff. You're made of the effort required to keep stuff in place. Now the consequence of all that emptiness, which is the strangest fact in this part of the ladder, and it is about your own body. If you removed the empty space from matter, if you compressed everything down so that the nuclei were packed against one another at the density they already have inside themselves, how much room would the human race take up? The density of nuclear matter is about 230 million tons per cubic meter. The mass of all 8.2 billion human beings is about 500 million tons. Do the division, And the answer is about 2 cubic centimeters. 2 cubic centimeters. Every human being alive on Earth tonight, the cube in Central Park, the 800 meters on a side, the shape you could walk around before your coffee cooled, compressed only by removing the emptiness that is already inside them, fits comfortably inside a sugar cube. You could hold the species in a teaspoon, and nothing has been taken away in that operation. No atoms discarded, no matter destroyed, every nucleus of every person still present and accounted for. All that has been removed is the nothing. 99.9999 and change percent of what a human body occupies is space. And if the space were folded away, everyone who's alive right now would fit in the hollow of your hand with room to spare. Run the same operation on the planet if you want the scale of it. Compress the entire Earth to nuclear density and the world, every ocean, every mountain range, every city and every forest, would be a sphere a few hundred meters across, something you could see from one end to the other, sitting where a small town used to be. That is not a thought experiment about destruction. It is a statement about what the Earth already is, a structure whose actual substance would fit inside a village, inflated to planetary size by nothing but the geometry of empty atoms. Nature does perform this operation, incidentally, on stars. A neutron star is exactly this compression carried out by gravity on a body the mass of the Sun, producing an object about the size of a city at nuclear density, where the emptiness has been squeezed entirely out of matter. There is one somewhere over your roof right now, spinning. But the version I want you to keep is the intimate one, not the astronomical one. Put your hand flat on the blanket, press down, feel the resistance, the plain, obvious solidity of a surface pushing back against your palm. There is no surface there. Your hand's atoms are almost entirely empty, the blanket's atoms are almost entirely empty, and nothing about the encounter involves anything touching anything. What stops your hand is the electromagnetic repulsion between electron clouds, a field effect that halts you about a nanometer short of any actual contact. You have never touched anything in your life, not another person, not a floor, not a face. Every point of contact you have ever felt was a force pushing back across a gap, transmitted through a structure that is, by volume, essentially vacuum. The solidity of the world is real as an experience and false as a description, and the emptiness of the universe that we found so frightening on the way up the ladder turns out to have been inside your hand the entire time, and we are still not at the bottom. The nucleus is not the floor either. Below it, the ladder goes down through the particles that make the proton, and past the last thing our instruments can resolve, and then continues, for another 19 rungs, into a region where the ordinary meaning of the word distance begins to fail. That is where we go next. It is the deepest place physics can name. It has a fence around it, and the fence is made of black holes. Come back to the atom for a moment and stand at its rim, the outer boundary of the electron cloud, the wall of the cathedral, because we are going to fall the rest of the way, and it helps to know where the fall begins. You are hovering at the edge of a hydrogen atom in your own hand. Below you, across a gulf of 63,000 to 1, the nucleus waits. Begin the descent. The wall recedes above you, and for a long time nothing happens at all. This is the emptiness, and the emptiness is most of the journey. The nucleus, when it finally arrives, comes fast, a dense knot of protons and neutrons, and you pass through it before you can register the arrival, and out the other side into a smaller dark. And here you are falling past things that no longer behave like objects at all. The quarks, which have no known size and never appear alone, bound so violently that pulling two apart creates new ones rather than separating them. Keep going. At about 10 to the minus 19 meters, 1,000 times smaller than the proton, you pass the last floor that anyone has ever seen. That is the resolution limit of the great particle colliders, the deepest that human instruments have ever probed. Down there, quarks and electrons still show no internal structure, no seams, no substructure. They behave at every energy we can reach as points. And that is not the bottom of the ladder. It is only the bottom of our eyes. Keep falling. Below the last measured floor, the counting continues in the dark. 10 to the minus 20, 10 to the minus 22, 10 to the minus 25. And by now, you have fallen further below the collider limit than the collider limit lies below a human being. Nothing marks the passage. There are no instruments here and no observations, only the equations, which keep working and keep saying that space continues. 10 to the minus 30, The floors go by like the floors of an elevator with no lobby, no lights, and no announcement. 10 to the minus 33, 10 to the minus 34, and then, at one point 6 times 10 to the minus 35 meters, physics stops. That number has a name, the Planck length. It is not a measurement of anything. Nobody found it with an instrument. It was built in 1899 out of pure constants, the strength of gravity, the quantum of action, the speed of light, by Max Planck himself, who was looking for units of measure that were not human. He wrote that such units would be independent of particular bodies and substances, and would necessarily retain their meaning for all times and all cultures, even extraterrestrial and extra-human ones. He was proposing the universe's own ruler, in a paper published before anyone knew what an atom looked like. And when you combine those constants into a length, the answer that falls out is 1.6 times 10 to the minus 35 meters, and it turns out to mark the depth at which our two great theories of reality stop working at the same moment. Below it, general relativity, the physics of space and time, and quantum mechanics, the physics of the very small, do not merely disagree. They both give answers that are meaningless. The concept of distance itself, as anything measurable, loses its grip. There is a companion number worth having, because it makes the depth of this place audible rather than merely visible. Alongside the Planck length there is a Planck time, how long light takes to cross one Planck length. It works out to about 5 times 10 to the minus 44 seconds. To feel the size of that gap, run it the other way. The number of Planck times that pass in a single second is enormously larger than the number of seconds that have passed since the Big Bang, larger by a factor of about 100 trillion. In the time it takes you to blink, the universe's own clock ticks more often than it has ticked seconds in its entire 14 billion year history. The bottom of the ladder is not only deeper than the top, it is faster than the whole age of the world. 2 clarifications, because both matter for what this place actually is. First, the Planck length is not a pixel. You will hear it said, constantly, that space comes in Planck-sized squares, that reality is grainy at the bottom, that we live in a universe with a resolution setting. That is a story, not a measurement. Nobody has ever detected a lattice, and the naive version has been tested. In 2009, a gamma-ray burst known by the designation 090510 sent us photons across 7 billion years of space at wildly different energies. Some models of a grainy spacetime predict that different energies should travel at very slightly different speeds, and over 7 billion years, even an infinitesimal difference would accumulate into a visible delay. The photons arrived within a fraction of a second of each other after 7 billion years in flight. A single burst of light from most of the way across cosmic history put harder limits on the graininess of space than any laboratory ever built. Whatever is down there at the bottom of the ladder, it is subtler than a grid. Second, what physicists actually expect at that depth is stranger than a grid anyway. John Wheeler in the 1950s argued that if you could look at spacetime at the Planck scale, you would not find a smooth stage or a neat lattice, but something violently unsettled. Geometry itself fluctuating, curvature boiling, connections opening and closing, a froth that he named quantum foam. Space, at the bottom, may not be a place things sit in. It may be a storm, viewed from far too close. And here is the fence. Suppose you wanted to check, to look directly at the Planck length, the way Rutherford's team looked directly at the nucleus. In principle, the method is known. To resolve something small, you need a probe of very short wavelength, which means very high energy. Run the arithmetic for the Planck length, and the energy required is so enormous, concentrated in so tiny a region, that the probe itself collapses into a black hole before it can return any information. Not metaphorically. That is what the equations say happens. Any attempt to see the bottom of the ladder creates an object that hides it, and if you prefer to brute force it with a conventional machine, the standard estimate for the size of an accelerator powerful enough is roughly the scale of the galaxy, a ring of magnets 100,000 light-years around. The floor of reality is defended twice over, by an engineering requirement the size of the Milky Way, and, if you somehow met it, by a black hole that swallows the answer. The universe's basement has no door. It is worth saying plainly that nobody knows what is actually down there, and that the 2 leading attempts to say disagree about the most basic question of all, whether the bottom of the ladder is a floor or a fog. One program, Loop Quantum Gravity, proposes that space near this depth is genuinely quantized. That area and volume come in discrete allowed values, woven from a network of relations, so that asking for a smaller region is like asking for half a photon. Another, string theory, dissolves the question differently. If the fundamental objects are not points but tiny extended strings, then there is nothing left to ask about below their length, because there is no probe smaller than the smallest thing. Loop theory says the ladder has a last rung. String theory says the ladder's rungs stop being distinguishable. Neither has been tested, and the honest state of knowledge is this. We can compute exactly where our understanding ends to 2 decimal places, and we cannot say what is on the other side of that number. This channel says, we do not know often, but rarely with this much precision about the location of our ignorance. Now the proportions, which are the reason we came down here, a single proton, that fly in the cathedral, already so small that 10 to the 28 of them fit in your body, is about 10 to the 20th Planck lengths across. Say that in a way that can be felt. There are more Planck lengths spanning one proton than there are meters in 10,000 light years. Inside a speck at the heart of one atom of one cell of one finger, there is, in the units the universe uses for its own bottom rung, a distance that would carry you 1/10 of the way across the galaxy. And now, at last, the count. This is the number we have been walking toward all night. From a human being, 1.7 meters, up to the far edge of the observable universe is a climb of about 26.7 rungs, 26.7 factors of 10. That is the whole upward ladder. Every star, every galaxy, every cluster, the end of greatness, the horizon itself. From that same human being, the same 1.7 meters, down to the Planck length is a drop of about 35 rungs. 35 against 26.7. The basement is deeper than the sky. Not by a little, by more than 8 full factors of 10. The distance from you down to the bottom of physics exceeds the distance from you up to the edge of everything we can see by a margin larger than the entire distance from you to the sun, expressed in the same terms. Every documentary, every planetarium show, every zoom-out video, every photograph taken by every probe we have ever launched has pointed your vertigo in the shorter direction. The long direction has been under your skin the whole time, unlit and unphotographed, and it does not end at the atom, and it does not end at the nucleus, and if you had fallen all night through your own hand, you would still be falling now. Which raises the question I have been holding back since Boke's classroom. If the ladder runs 27 rungs above you, and 35 rungs below you, then where exactly are you standing on it? Not small, not at the bottom, somewhere with an enormous amount of room underneath. The arithmetic is simple and nobody ever does it, and when it is done it produces a description of a human being that I have never heard said out loud in any documentary about our size. We're going to do it now, and it is the second answer to tonight's question. Here is a test you can run in your head, lying exactly where you are, and it is the cleanest way I know to feel what the 2 directions of the ladder actually mean. Earlier tonight we worked out that it would take about 5 times 10 to the 26 human beings, laid end to end, to span the observable universe. Take that number, the whole width of everything visible, expressed in units of you, and now use it to shrink yourself. Divide your height by it. Reduce yourself by exactly the factor that separates a human being from the edge of the cosmos. You have just performed, on your own body, the entire upward ladder in reverse, every rung we climbed tonight, the planet, the star, the giants, the galaxy, the clusters, the smoothness, the horizon. All of it, applied to you at once, as a shrinking. How small are you now? About 3 times 10 to the minus 27 meters. And here is the thing to feel. You're still nowhere near the bottom. Having shrunk by the entire width of the observable universe, you would still be 100 million times larger than the Planck length. Still falling. Still with 8 rungs of ladder beneath you, unexplored, unlit, and, as far as any instrument can say, real. You could take the whole visible universe, use it as a shrink ray, apply it to yourself in a single stroke, and you would not reach the bottom of your own hand. That is the proof, in the plainest form I can give it, that the inward direction is the long one. Now someone will object, and the objection deserves an answer, because it is the reason nobody notices any of this. Why measure in factors of 10 at all? Why not measure the ordinary way by subtraction? Subtract, and the whole argument evaporates. An atom and a human being are, in absolute terms, practically the same size compared to a galaxy. The difference between 10 to the minus 10 meters and 1.7 meters is nothing next to a light year. But that is exactly the blindness. Additive thinking treats every quantity smaller than a kilometer as effectively identical, and so it cannot see that an atom stands as far above the Planck length as a galaxy stands above a grain of dust. Ratios, not differences, are how physics compares scales, because the laws themselves care about ratios. How many atoms across, how many wavelengths, how many times bigger. The ladder of size is a ladder precisely because every rung is the same size as every other, in the only currency the universe honours, which means the count is fair, and the count says 35 down, 27 up. There is one more way to make the fairness of this vivid, and it is Boke's staircase, drawn properly at last. Imagine the ladder as a flight of stairs, one step per factor of 10, each step the same height as every other because each step is the same multiplication. Stand on your step. Above you, 27 steps rise to the edge of the observable universe. Step 1, the room. Step 3, the city. Step 7, the planet. Step 9, the sun. Step 16, the galaxy. Step 27, the horizon of light. That is the entire upward journey. 27 steps, and it contains every object anyone has ever photographed or named. Below you, 35 steps descend. Step 4 down, a cell. Step 6, the pollen grain at the midpoint. Step 10, the atom. Step 15, the nucleus. Step 19, the last floor any instrument has ever lit. And then 16 more steps into the unlit dark before the Planck floor. Same staircase, same size of step. One flight of 27 going up, and one flight of 35 going down, and the whole of astronomy lives on the shorter flight. So let us find the exact centre. The true middle rung of the ladder of size, the length that sits the same number of factors above the Planck length as it does below the edge of the observable universe. It is straightforward arithmetic, and the answer comes out at roughly 10 to the minus 4 meters, a tenth of a millimeter. That is the midpoint of everything. Not a star, not a planet, not a molecule, a tenth of a millimeter, a speck at the very limit of what an unaided human eye can see, and only in good light, and only if you know to look. The geometric centre of all size is a fleck of dust on a windowsill. It is worth naming the tenants of that address, because they are humbler and stranger than you would expect from the middle of the universe. A grain of pollen sits there, a dust mite, a paramecium in a drop of pond water. The width of a fine human hair sits just below it, a grain of table salt just above. And one more thing lives at that exact scale, and I have found no way to say it that does not stop me for a second. The human egg cell is about a tenth of a millimeter across. It is the largest cell in the human body and the only one a person can see without any instrument at all. It is also, to within the roughness that estimates like this allow, the object at the precise centre of the ladder of size. Every one of us began as an object sitting at the exact midpoint between the Planck length and the edge of the visible universe. You have been on both halves of the ladder in one lifetime, and you started at the balance point, and you did not stay there. You grew 4 full factors of 10 upward from that cell, which places a full-grown human being not at the midpoint of the ladder of size, but about 4 rungs above it. Say it plainly, because it is the second answer to tonight's question, and it is the exact opposite of the answer everyone is given. On the ladder of size, honestly counted, a human being is not small. A human being is large. We stand above the middle of everything, nearer, in the only measure that lets these scales be compared at all, to the entire observable universe than to the smallest length physics can name. The distance from you up to the edge of the cosmos is the shorter of your 2 horizons. Somebody standing on the true midpoint of the universe's sizes would have to look up at you. Let that in slowly, because it is the reversal the whole night has been walking toward. Every documentary told you that you are a speck against everything. The arithmetic says you are a giant leaning over an abyss. Both statements use real numbers. They point in opposite directions because they are measuring different things. One is measuring how much room you take up, and the other is measuring where you stand. And the reason the second has almost never been said is simply that nobody bothers to count the direction that has no photographs. It also reframes something we passed over quickly. When we said, on the way up, that a bacterium is unimaginably small, 6 rungs below a human, invisible, a thing you need a microscope to believe in. We were speaking from the same blindness. Count a bacterium's position honestly, and it stands about 29 rungs above the plank floor, which is to say a bacterium is further from the bottom of the ladder than you are from the top of it. The single-celled organism in a drop of pond water lives, like us, in the upper half of everything. Everything alive does. The entire biosphere, whales, redwoods, bacteria, viruses, occupies a narrow ribbon of rungs in the ladder's upper region, and there is not one living thing on Earth, at any size, that comes close to the ladder's lower half. Life does not merely fail to reach the bottom. Life does not even reach the middle from below. It only touches the midpoint at the moment of its beginning, in a cell. And before anyone assumes this is a trick of the estimates, it is not fragile. Suppose the observable universe turns out to be somewhat larger than we think. Suppose the true floor is not the Planck length, but a few orders of magnitude below it. Suppose you are taller or shorter than average by any amount you like. Push every number, in the direction least favourable to the argument, by several factors of 10, and a human being remains above the centre of the ladder. The asymmetry is 8.5 orders of magnitude deep. There is no plausible correction that closes it. We are robustly on the upper half, so the question sharpens rather than closing. Two things are now sitting on the table and neither is comfortable. The first, if we stand above the ladder's midpoint and if the ladder has a floor 35 rungs down and a ceiling 27 rungs up, why here? Is it luck that the only creature we know of that has ever measured the ladder is standing at that particular height on it? Or is there a reason, written into the physics, that anything capable of asking tonight's question must stand more or less exactly where you are lying right now? And the second, which is worse, everything tonight, every fraction, every division, the decimal point and the 80 zeros, has been measured against the observable universe. But the observable universe is not the universe. It is the part whose light has had time to arrive. There is more out there, and nobody knows how much more, and the honest answers range from at least 250 times wider to a number with no upper bound at all. Which means the denominator of your smallness, the thing we have been dividing you by all night, may not be a number. It may not exist. Both questions get answered next, and they answer each other in a way I did not expect when I started assembling this. In 1926, a British biologist named JBS, Haldane published a short essay in Harper's Magazine, and he opened it with giants. He was thinking of the giants in Pilgrim's Progress, Pope and pagan, 60 feet tall, 10 times the height of a man, and he pointed out with obvious enjoyment that they could not have existed for an afternoon. Make a man 10 times taller, and every dimension multiplies. His weight goes up by 1,000, because weight follows volume, which grows as the cube of the length. But the cross-section of his thigh bones, which must carry that weight, only goes up by 100, because area grows as the square. So the giant's bones bear 10 times the load per square inch that yours do, well past the breaking strength of bone. Haldane's conclusion was that Pope and pagan would have broken their thighs every time they took a step. The essay was called On Being the Right Size, and it is, a century later, still the clearest statement of why the ladder of size has a livable band on it. The rule is called the square cube law, and it governs everything with a body. It is why the largest land animals that ever lived had pillar legs and slow gaits, why an elephant cannot jump and a flea can leap 100 times its own length, why, as Haldane famously noted, you can drop a mouse down a 1,000-yard mine shaft, and it will get a slight shock and walk away, while a horse dropped down the same shaft splashes. It is why there are no wolf-sized spiders. Insects and their relatives breathe by letting air diffuse down tubes into their tissues, and diffusion simply stops working past a few centimetres of body depth. The largest animal that has ever lived, the blue whale, gets to be 30 metres and 150 tons only by cheating, by living in water, which holds up the mass that its skeleton could not. On land, under this gravity, bodies have a ceiling, and it is nowhere near the height of a Pilgrim's Progress giant. So gravity puts a lid on how far up the ladder a body can climb. What puts the floor under it? Noise. Go far enough down the ladder and the world stops being still. At the scale of large molecules, everything is being ceaselessly battered by thermal motion, the constant, random kicking of surrounding particles, the same phenomenon Einstein explained in 1905 when he showed that the jiggling of pollen grains in water was proof that atoms exist. Down there, a structure that is supposed to hold information, or hold a shape, or carry out a sequence of operations reliably, is standing in a permanent gale. You can build machines at that scale. Cells are full of them, and they work. but they only work by being large enough and redundant enough to hold their state against the storm, go smaller, and the storm wins. There is a flaw under complexity, and it is made of heat. And then there is the ceiling above thinking specifically, which is my favourite of these limits because it is so rarely mentioned. Suppose you wanted to build a brain much larger than a human one, a brain the size of a planet, say, with correspondingly astronomical numbers of neurons. Nothing in biology forbids the parts, but signals in nerve tissue travel at a maximum of about 120 meters per second, and that speed is set by chemistry, by ions crossing membranes, and cannot be argued upward. In a human head, a signal crosses the whole brain in a few thousandths of a second, which is why thought feels immediate. Scale that brain up to planetary size and a single signal crossing the structure takes more than a day. One thought, one full pass of information across the mind, would take weeks. A planet-sized brain would not be a greater mind, it would be a slower one, thinking a handful of thoughts per century, outpaced on latency alone by the phone on your bedside table. Put the three limits together, and something surprising falls out. Gravity caps the size of bodies. Thermal noise floors the size of reliable machinery. Signal speed caps the size of anything that has to think as one whole. Between the floor and the ceiling there is a band on the ladder, a fairly narrow band, in which matter is permitted to be complicated, mobile, and quick enough to hold a thought together. That band is where you are lying. It is not a coincidence that the only object we know of that has ever counted the rungs of the ladder is standing in that band. It is close to a requirement. The universe did not place us above the midpoint of all size as a courtesy. Physics arranged the ladder so that anything capable of noticing the ladder would have to stand roughly here, which sets up the last and strangest measurement of the night, and it is not about size at all. It is about how unusual an arrangement you are. The average density of the universe is about 6 hydrogen atoms per cubic meter. That is the mean. Take the whole thing, galaxies and voids together, and stir. 6 atoms in a volume the size of a washing machine. A human body runs at about 1,000 kilograms per cubic meter, the density of water, near enough. Divide one by the other, and a human being is roughly 10 to the 29 times denser than the universe's average. 100 billion times. And that is only the beginning of the strangeness, because the matter we are made of is itself a rounding error in the inventory. The best current accounting puts the universe at roughly 68% dark energy, 27% dark matter, and about 4.9% ordinary atomic matter. Everything in the periodic table, every star, every planet, every person, in that last 5%. And within that 5%, the overwhelming majority is thin gas drifting between the galaxies, never gathered into anything. The fraction of the universe that has been assembled into structures as organized as a star is small. The fraction assembled into anything as organized as a cell is not meaningfully computable. Whatever else a human being is, it is one of the least typical things this universe does with matter. There is a way to hear how unusual that is. Take a cubic meter of the universe at random, genuinely at random, which means almost certainly somewhere in the enormous emptiness between galaxies, and you will hold 6 atoms drifting, having drifted for billions of years, and likely to go on drifting for billions more without meeting anything. Take a cubic meter from where you are lying, and you hold something on the order of 10 to the 29 atoms, arranged into cells, arranged into tissues, arranged into an organism, each one of them replaced and rebuilt on a schedule, the whole assembly maintaining itself against the constant tendency of matter to fall back into the average. That is the actual comparison. Not big versus small, but a stirred emptiness versus a structure so improbably organized that it is currently thinking about the emptiness. If a random sample of the universe is a bare room, you are a library with a librarian who is awake. And now the problem that has been waiting all night. Everything, every fraction, every division, the 80 zeros, was measured against the observable universe. But the observable universe is not the universe. It is a horizon, the sphere from which light has had time to reach us in 14 billion years. It is not an edge, and nothing is there. It is centered on you personally. Every observer has their own, the way every ship at sea has its own horizon. And a galaxy sitting at our boundary sees us at theirs, with another 46 billion light-years of universe stretching out behind it that we will never see. How much more is out there? The honest answer comes from geometry. The universe's spatial curvature has been measured, and it is indistinguishable from flat. flat to within about 2 parts in 1,000. If the universe were finite and closed, curving gently back on itself like the surface of a sphere, that curvature would show. It does not. And that failure to show puts a flaw under the size of the hole. A widely cited analysis concluded that the entire universe must be at least about 250 times the radius of the part we can see, which is at least 15 million times the volume. That is the conservative reading. Inflationary cosmology, our best account of the universe's first instant, routinely produces numbers like 10 to the 23rd times larger. And the simplest reading of perfect flatness is the one that ends the argument, a universe that is infinite. Follow that last possibility all the way, because it does something to tonight's question that no other number can. If the universe is infinite, then your share of it is not 1 part in 10 to the 81st. It is not a very small number at all. Any finite thing divided by infinity is exactly 0. Not approximately, not for practical purposes, exactly as a matter of arithmetic. And so is the Earth's share, and the Milky Ways, and the entire observable universes, 93 billion light-years, 2 trillion galaxies, all of it, is likewise exactly 0% of the whole. The scariest available answer to how small are we is not a very small number. It is the discovery that the question may have no denominator. While we are here, we should meet the idea that always arrives at this point in the conversation, because it is sincere, and it deserves a real answer rather than a smirk. The idea is that the ladder repeats, that atoms are little solar systems, that our universe might be a single atom in some larger being, that the whole structure nests forever in both directions. This is not a modern internet fancy. It has a genuine pedigree. In 1904, the Japanese physicist Hantaro Nagaoka proposed a Saturnian atom, electrons ringing a nucleus like moons. Early popular drawings of the atom made the resemblance explicit, and those drawings are still on classroom walls. And in 1908, the Swedish astronomer Carl Charlier published a serious hierarchical cosmology in which stars cluster in clusters without end. The modern version, the side-by-side images of the cosmic web and a slice of brain tissue, captioned as if the case were closed, descends directly from these. The physics answers in 3 moves, and they are the same 3 we have already earned tonight. First, atoms are not solar systems. Electrons do not orbit. They occupy standing patterns, and the resemblance died in the 1920s along with the picture that produced it. Second, the ladder cannot repeat because physics is not the same at every scale. The strong force rules below the nucleus, electromagnetism through our middle band, gravity above the planetary rungs, and the constants of nature stamp absolute sizes onto matter. A hydrogen atom is the same size in every galaxy. That fixed size is a fingerprint proving there is no zooming out into a copy. And third, the cosmic web really does share statistical features with a network of neurons. Both are networks, and networks obey network mathematics. But the resemblance is arithmetic, not kinship. A signal crossing one filament of the cosmic web would take hundreds of millions of years. The end of greatness closes the case observationally. Above 300 million light-years, the hierarchy stops. The ladder does not repeat itself. It has a top floor of structure and an unlit basement, and we are on it exactly once. And there is one more reason to be careful with the nesting idea, which is that it is the most comforting story available about our size, and comfort is exactly what should make us check our arithmetic hardest. A universe that repeats forever in both directions is a universe where smallness never means anything, because there is always someone smaller and someone larger, and the whole question dissolves into an infinite regress that nobody has to feel. The real ladder does not offer that. It ends in both directions, a defended floor 35 rungs down and a horizon 27 rungs up, and we are on it once, at one height, with nothing beneath us but physics we cannot reach, and nothing above us but distance we cannot cross. That is a harder picture than the fractal one. It is also, on all present evidence, the true one. So hold both halves of the night at the same time now, and let me put you where the whole picture is visible. You're standing on a staircase in the dark. It hangs in nothing, going up and going down, and each step is a factor of 10. Look up. 27 steps rise above you, and you can see them dimly, each one lit by what stands on it. The room, the city, the planet, the sun, the giants, the galaxy, the clusters, until the highest visible step glows faintly with the light of everything there is to see. And past that step, More stairs, unlit, going up into a dark that has no measured end. At least 250 times farther, possibly without end at all. Now look down. 35 steps descend beneath you. Cell, pollen grain, atom, nucleus, the last lit floor at step 19, and then 16 further steps into a dark that no light of any kind has ever entered, ending at a floor nobody can reach without creating a black hole. 2 darknesses, one above, one below, and between them, on one step, at a height nothing chose, a warm object about 1.7 meters tall, made of 7 billion atoms borrowed from dead stars, lying still in a room, looking both ways. That is the picture. Everything is now on the table, which means we can finally, properly answer the question we started with. Go back to the dot. February 14th, 1990, 6 billion kilometers out, a pale point of light sitting inside a band of scattered glare, occupying 0.12 of 1 pixel. Everyone who has ever lived is in that pixel. We have spent tonight finding out what it is actually a picture of, and now we can say, 3 times, 3 different ways, all of them true. The first answer is the one the photograph implied, and we made it exact. By volume, against the observable universe, a human being is about 1 part in 5 times 10 to the 81, a decimal point, 80 zeros, and then you. And that answer was generous, because it divided you by the visible portion only. The whole is at minimum 250 times wider in radius. By the standard inflationary reckoning, a factor like 10 to the 23. And if space is flat in the simplest way the measurements suggest, without bound at all, in which case the true fraction is not a small number, but exactly 0. That is the first answer. Against everything there is, we do not register, not faintly, not at all. The second answer is the one nobody tells you, and it is not softer, it is stranger. Measured not by how much room you take up, but by where you stand, counted honestly in factors, which is the only currency in which such scales can be compared, a human being stands above the middle of the ladder of size, 27 rungs above you to the edge of the visible, 35 rungs below you to the floor of physics. The direction with all the photographs is the short one. You could shrink yourself by the entire width of the observable universe and still be 100 million Planck lengths from the bottom of your own hand. And the exact centre of all size, the true midpoint between the largest and the smallest, is 1/10 of a millimetre, a mote of pollen, a dust mite, and the human egg cell, the object each of us briefly was. We start at the balance point of everything and grow upward from it. That is the second answer. On the ladder you're not a speck, you're a giant leaning over the deeper half. And the third answer is not a size at all, which is why it took the whole night to get to. You're 10 to the 29 times denser than the average cubic metre of the universe. You're made of 7 billion atoms, which is thousands of times more parts than the visible universe has stars, every star behind every star, all the way to the horizon, outnumbered by the contents of one hand. Those atoms were manufactured inside the giant stars we walked past on the 4th rung, and scattered by their deaths, and they have been assembled temporarily into a structure that maintains itself against the universe's constant pull toward the average in a narrow band of the ladder, bounded above by gravity, below by heat, and sideways by the speed of a nerve signal, which is the only band where matter is permitted to be complicated enough to think. Everything on this staircase is made of the same physics. Exactly one thing on it, so far as anyone knows, has ever counted the steps. That is the third answer. By extent we are nothing. By position we are large. By arrangement we are close to unique. And the last of those is the only one that required the universe to do anything difficult. It is worth noticing that all 3 answers were true simultaneously, the entire time, and that they only appear to contradict one another because each is measuring something different. The first measures extent, how much of the universe's volume you displace. The second measures position, where on the scale of all sizes you happen to sit. The third measures organization, how far your matter is from the average state of matter. Nothing in physics says these 3 should agree, and they do not. The mistake underneath the entire genre of cosmic humility storytelling has been the quiet assumption that extent is the only one that counts, and that a thing's importance can be read off its diameter. Nobody would apply that rule to anything they cared about on Earth. We applied it to ourselves the moment we saw a photograph. I will label the speculation clearly, as this channel always does, because there is a tempting further step here, and it is not established physics. In 1937, Paul Dirac noticed that certain ratios in nature, the strength of electricity against gravity, the age of the universe in atomic units, keep landing near the same enormous number, around 10 to the 40th, and he suspected the coincidence meant something. His particular hypothesis did not survive. The measurements went against it. But the instinct behind it, that ratios are where the meaning hides, is the same instinct that ran tonight's arithmetic. There is a firmer version in modern physics called the holographic bound, which limits how much information any region can contain. For the observable universe, the ceiling is around 10 to the 122 bits. Your brain has, generously, 10 to the 15 synapses, against the universe's information ceiling that is nothing whatsoever, and yet the ceiling was computed by exactly such a brain, on a planet, in an afternoon. And there is a third speculation, softer still. If the band we occupy is really set by gravity, heat, and signal speed, then any observer anywhere, on any world, around any star, in any galaxy in that Hubble keyhole, must stand at roughly our height on the ladder, which would mean that everything in this universe that has ever understood its own size has been about your size while understanding it. That is not proven. It is consistent with everything we know. So, our true size in the universe. It is far scarier than we were told, and I want to be exact about why, because it is not the reason the documentaries give. It is not scary because we are small. Small was always the easy answer, and it is only half of an arithmetic problem. It is scary because small turns out to be the wrong word entirely, because size, examined honestly, stops working as a way of ranking things. The universe has no address for us and no denominator for our fraction. It also has, so far as anyone can demonstrate, nowhere else where the ladder is being counted. Both facts come out of the same measurements. You do not get to keep only one, and I think that is a fair thing to fall asleep on, because it leaves the question open in the right direction. We know exactly how much room we take up, to 80 decimal places of nothing. We know where we stand, and it is higher than anyone told us. What we do not know, what nobody knows, is whether the third answer is common or rare or singular, whether other steps of other staircases have someone standing on them tonight, looking both ways, whether the universe, which keeps no ledger and marks no places, has done this once or endlessly. There is no measurement for that yet. There may never be. Which brings us back, one last time, to the photograph. A pixel, and then nothing. That was the shape of the story we inherited, the dot dissolving into the dark, humility and hush and the closing music. It is a good story, and it is incomplete, and you now know both directions of the ladder well enough to see what is missing from it. Because the interesting thing about that pale point of light was never how little of the frame it occupied. The interesting thing is that inside it, 6 billion kilometers away, at the bottom of a gravity well, on a wet rock going around an ordinary star in the suburbs of one galaxy among 2 trillion, something had built the camera. Something had aimed it, waited 9 years for permission, and turned it around specifically to see how small it would look. Nothing else in the frame did that. Nothing else in the frame could. A pixel that looks back. That is what the picture is of, and it is the only thing in it that the universe has never been shown to do twice. Sleep well. The staircase will still be there in the morning, 27 steps above you, 35 below, and you exactly where you are, which turns out to be higher than anyone said.